So the example that we'll be working out, it's quite a long example because of the generality that we'll do it in, is if you're given data, and let's say the data you're given is you have a bunch of x values and a bunch of y values. So these are one-dimensional input and one-dimensional output values. So suppose you have given data x1, y1, x2, y2, and so on, up until the number of data points that you have, xd, yd. And if you try to plot these data points, let's say they look maybe something like this. The question that you want to solve is, can you try to find a line that sort of best approximates these data? So that's the problem, is to find a best fit, whatever that means, straight line. Let's say of the form y equals mx plus b. Now, if we wanted to actually try to solve this problem, and suppose that all of these points actually lied on this line, we would want to solve this entire system. Now, m and b are our unknowns. We don't know the slope. We don't know the y-intercept. So we'd have y1. We want to set it equal to mx1 plus b. Similarly for y2, our second data point, mx2 plus b. And we keep going. yd equals mxd plus b. Now, in general, this is an over-constrained system because we have d equations, and if d is relatively large, in particular if it's bigger than 2, if it's relatively large, it's very unlikely for us to find a solution to this problem. We can rewrite this problem as a matrix equation by saying that we have the vector y, which is the vector of our data points. In fact, let me even write y as a column vector. So let's write it like y1 all the way to yd. And if we notice this, our coefficients are always being added in a linear fashion. And the only thing that's changing is the value of x1. So you could actually write this as a d by 2 matrix acting on the vector mb. Now, what should this matrix be? We want it to satisfy the equation y1 equals mx1, so x1 has to go in this column, plus b times, what's the only thing that's going to leave b exactly where it is? The number 1. And the same thing here, if we had y2, we would want to write y2 equals m x2 plus 1 times b, and so on, all the way down to xd and 1. So this matrix equation, which we can write as y vector equals a, and I don't want to write x as we did before because I don't want to conflate it with the data points that are also labeled by x. And so instead we'll write this as a xc. So this is the system that we would like to solve, but we know that there is in general no solution to this problem. So what can we do? Now in this case, the column space of A happens to be a two-dimensional subspace of R what? Of RD. So the column space of A is a two-dimensional subspace of RD. So we can actually draw something like this, although the space it's in might be significantly larger. And we have the vector y somewhere out here. In general, it's not in the column space. In general, this line does not go through every single one of these data points. So we have some vector y, and instead of trying to solve this specific equation, which in general is unsolvable, we can project y onto this subspace W. And we can solve that associated system, and then we'll say what that means in a moment. In fact, actually, we can say what it means right now. If we take the difference of these two vectors, y minus this projection, what are we minimizing? So an arbitrary vector in this subspace, let's write W as an arbitrary vector in the subspace is a linear combination of these columns. So let's write that linear combination as M, suggestively, AE1, which is the first column of A, which is just all of these x data points, plus B times the second column of A. And we want to minimize the distance between our data set, our data vector y, with this vector. So in other words, if we take this difference, let's replace this with w for now, because let's imagine we don't yet know that this is the projection. So this difference is trying to minimize y minus m AE1 plus b AE2. And if we look at what each of these components give you, then this equals, let's square this, just so we don't have to deal with square roots. Then this is the sum. So first let's take an arbitrary ith component here. It's yi minus m times xi plus b. And that's it. And then we take the sum of these squares, because that's what this means, and we sum over all I from 1 to d. So we want to minimize this expression. In other words, we're taking our actual data set y, and we're taking this, which is our best fit curve, using our data set x. And so we're trying to minimize all of these distances. So these are actually the vertical distances between the best fit curve and this line. It's the vertical distances, because this is saying our y data point minus the value of this line at that point, and we take that distance, that difference, which is this little vertical height, we square that height, and then we add up all of these heights, and we want to minimize that expression. So the solution to this least squares problem is graphically given by an expression like that. And we know how to solve this. To solve this, we apply our previous theorem. And we know that to solve this, we can solve instead A transpose A equals A transpose AX equals A transpose, and X is Xi. Let me write this as Xi, and A transpose Y. So this is the problem that we want to solve, and we want to solve this for Xi, and Xi is our vector of unknowns. So in order to do this, we have to write down what A is. We already know what A is. We have to write down its transpose. We have to multiply those two things. There's a lot of things we have to calculate. So let's do that on a fresh board space.